Hello everybody! Today we will be continuing the topic of the damped free vibration. I mean, we have the problem of the damped free vibration, and we are still in the problems connected with the single degree of freedom systems. And from the previous videos we remember that quite good linearized model of such a system is as follows. I mean, we have the sprung mass with the stiffness K and the damping coefficient, I mean the viscous or viscosity coefficient C, and the governing equation of such a problem is as follows. I mean, we have due to the Newton's second law, we have the inertial force. Here we have the damping force and the restoring force K of x, and because we are speaking about the free vibration, here we have the zero at the right hand side. And today we will introduce some interesting measure of the damping in the system, which is called logarithmic decrement. It means it's a logarithmic decrement. It will be some measure of the damping in our system, which will be quite useful and which will be quite easy to calculate. Okay, and how to deal with that measure? Firstly, we have to again, let's say, solve our governing equation. It means we are, like always, dividing by the mass. We are getting such an equation. If we will introduce our typical substitutions, we are getting such a thing, where our governing equation is expressed in the form of the displacement. And we remember that typically we are predicting the solution in the form of the exponential function with the RT, and due to the characteristic polynomial, which will be the effect of the application of that thing, we are getting two roots of our for our system, which should be treated as eigenvalues of our problem of damped free vibration. Okay, and we remember from the previous videos that that solution will be as follows. I mean, it will be minus h, I mean the half of that coefficient, plus minus I as an imaginary unit, and here we have omega 0 square minus h square, which last time was called omega h. I mean, we are getting such a thing, omega h. And the solution, it will be composed of two linear terms, because we have the two roots. I mean, we have to, like last time, we have to predict two elements. I mean, it will be such a thing. We have to applicate that element. It will be minus h minus omega h. Everything will be multiplied by time from that component, plus C2 times E minus h plus h I t. I forgot about I here. Of course, here we see also I. And everything is put in parentheses. Okay, and due to the rules how we should deal with the powers, we know that it will be such a thing. I mean, it will be minus h, because the sum of the power, it will be product of the powers, and we are getting the sum in the power will be product of the powers, and we are getting that it will be minus I omega h t, and the same is visible here. I mean h t times E plus I omega h t, such a thing. And we see that we have the common factor here. And also from our previous videos, we remember that if we have that elements, I mean the C1 times exponent function of minus I omega h t plus some another exponential function of plus I omega h t, and also due to the Euler formulas, we know that we are able to rearrange that equation into the form of linear combination of the sine and cosine component. I mean, it will be, let's say, some d1 times sine omega ht plus d2 times cosine omega h t. Such a thing. Let's close that braces and let's close that big brace. Okay, and it's our form of our solution. And also we can make some plot of that function, and we see that it will be some sine component. I mean something which give us the periodic changes of the function, and also we have something which which constantly decrease the amplitude of our vibration. Okay, I mean here we have the t as a time, here we have the x of t, and here we see our solution, which will have a following form. And as we see, that changes are constantly decreasing, and the curve which describes these changes is, as I mentioned before, is exponential of minus ht. Okay, and what will be that measure which I mentioned previously? The logarithmic decrement, let's say delta, it will be the natural logarithm of the ratio of the two amplitudes. I mean the A1, let's say, and A2. I mean, we are taking, let's say, that amplitude, A1, and we are taking the next amplitude, A2. The difference between those two amplitudes, it will be TH. I mean, it will be connected with the angular frequency in such a formula. I mean, it's a period of the time vibration. I mean, value exactly given by omega h. Here we have some unknown time t0, but in the moment we will see that the position of the first maxima of that plot is not especially important. It means that the global position, I mean from the origin of the second point of the amplitude A2, it's T0 plus TH. Okay, and if we want to compute that thing, firstly we need to find the ratio between A, N and A2, and it will be, as we see, it will be the value of our solution at the point T0. I mean A1 is a solution at point T0 over the solution at that point. I mean exactly here. It means it will be T0 plus TH. I mean exactly after one period. Okay, and if we want to compute it, we have to put the data. Okay, it means as a numerator we have minus h T0, as a denominator we have the minus h e to the minus h T0 plus TH, and here we have our D1 sine omega h T0 plus D2 times cosine omega h T0. If we are talking about the denominator, sorry, we have, of course, D1 times sine omega h T0 plus TH. If we are talking about second component, will be exactly the same. I mean, it's a cosine omega h T0 plus TH. Okay, what can we say about that thing? It's visible that we have the sine function after one period, and also we have the cosine function after one period. We know that sine and cosine function are getting the same values which are distance about TH. It means that the sine or cosine omega h T0 plus TH is exactly the same as a sine omega h T0. We can apply that formula and we are getting something which will be simpler. Simultaneously, I will use the rules how to deal with the exponential function. If we see the division of such a function, we are able to move the exponential function from the denominator to the denominator, but we have to change the sign of the power. Okay, or I mean the argument of the exponential function, and we are getting plus ht0 plus th times e to the power of h times t0. And what we are getting here? We are getting here exactly 1. In the moment we will see that one. I mean we have the sine omega h t0 plus d2 times cosine omega h t0, and everything will be divided by d1 times sine omega h t0 plus d2 cosine omega ht0. Okay, and it means that we can simplify that equation because in the numerator and denominator we are seeing exactly the same thing. And it means as a final result we are getting the difference of the powers of that exponential functions, because due to the rules how to deal with such an expression, we are getting that it will be plus ht0 plus th in the braces minus ht0. It means as a final result we are getting hth, such a thing. Okay, and in the next step we can compute the delta, which will be the logarithm of EHTH due to the rules how we should deal with the logarithm. We see that it will be exactly h times th. And we see that delta, it will be quite good estimator of the damping in the system because delta is proportional to the h. Also, we can consider the situation when we are getting the A1 to the some subsequent number. I mean, when we are dealing with the x t0 over x t0 plus some bigger numbers of the periods. And generally, the result will be exactly the same, because if we are talking about that component, the same rule can be applied. I mean, we are getting one if we are talking about that part, because the same rule can be applied here. The difference, the only one difference will be exactly here. I mean, we will have the e to the power of minus ht, it will be the effect of that thing. If we are talking about that component, there will be the h times, and here we have the difference, because it will be the argument t0, but we have to add the n times th. It's the difference between our case, which we started at the beginning, and the case when we are considering the bigger number of the periods, the an amplitude. And as an effect, we are getting that it will be, I will take it in the brace, and as an effect we are getting that it's a e to the power of h n th. I mean, here we have the bigger number of the periods, and as a delta n, let's say, I mean after bigger number of periods, it will be n times h th. It means that it's a multiple of the, let's say, fundamental delta of our element. It means that if we want to compute the logarithmic decrement, we can use that basic formula, but also if it will be more convenient for us, we can consider the bigger number of periods, and then delta, it will be connected with the delta after bigger numbers of periods by such a simple formula. As you see, it isn't especially complicated. In easy way, we are able to find what is the damping coefficient in some damped free vibrating system. Thank you guys, see you next time.